going to talk about the climate and the importance of satellite data to climate. Tell me why satellites especially is so important for specifically climate measurements.
So as you can see, this is the distribution of the global surface station network that does measurements of the atmosphere, the status of the atmosphere. But you can see that this is very much land-based, so we only have very few measurements of the oceans. But the oceans are very important, if not the most important part for the climate system. So this is why satellites are so important, because you can see here we have an aerial coverage. You can see the entire Earth, not only these dots here and there, but this gives us a much more complete picture of the system, so it's much easier to analyze and to see what's going on.
So it's very biased. If you just look at the land stations, they're clustered almost entirely over the continents, and yet there's the rest of the planet. You want to see that as well.
Yes, that's exactly how it is.
And when you're looking at the oceans with respect to climate, what sorts of data do you need? What sort of data is important?
There are a whole bunch of data that are important for the oceans, but what we can measure from satellite is, for example, the sea surface temperature, the sea surface height, and the ocean color, which gives you information about chlorophyll concentrations and nutrients in the water, which is very important for environmental monitoring as a whole. So knowing about nutrients and about chlorophyll in the water, you can also draw conclusions on the carbon cycle, which is obviously very important for the climate. So since climate is happening on long time scales, we also need data that represent these long time scales. And in that sense, it is not enough to just put the time series together as we have them, but we also need to make sure that we are kind of measuring the same thing, because sensors are changing over time, they are developed, and we need algorithms to retrieve the geophysical parameters from what the satellite actually measures. And these retrieval algorithms also develop over time. And so once we have this long time series and made sure that we have this what we call homogeneous time series, we need to apply a stable algorithm to the entire time series until we can come up what we call a climate data record. And this is what we can do climate monitoring and climate analysis from.
So you've got two problems then. The first one is that you're learning how to better process data and look at data, and so you need to use those new processing methods for all of the data, even the historical data. Yes. And then you also have the problem that you might have different measurement techniques that overlap with each other.
Yes.
Tell me a little bit about that process.
Yeah. You can see here, it's one of the same method of measuring a thing, but you can see each line represents a new sensor of the same time.
So we have time along the bottom, so we've got 1988 going all the way to 2004.
Exactly.
And what are we seeing up the side?
This is the measurement of the brightness temperature of the global oceans. This is what we can see here, and obviously it should, I mean, if you have two lines in the same time frame, it should represent the same thing, because it's the same thing is measured. But you can see there's a difference in the sensor, and this is not because the environment is different, but because the sensor reacts differently, and this needs to be accounted for when we produce long time series. And this can be done using statistical methods and using ground truth information. And this is why it is important that we have this information in situ measurements, and that we have a sufficiently large overlap once the sensor is changing, so that we can do all this adaptation and produce this time series. So this one is what we call an intercalibrated time series. This is something that can be used to produce climate data records.
So all these sensors that are used up here, they're the same model of sensor, and they're looking at the same thing.
Yes.
And so they should all see the same thing, and it's not that they're wrong, it's that each one has something slightly different in the sensitivity. So there's tiny variations, but there's still, you're after the one authentic measurement.
Yes.
And so you have to work out those differences to work out what that original measurement should be.
Yes, that's exactly the point.
And so you can see here, I mean, it's believable that they're measuring the same thing, isn't it? Because they go up and down at the same time.
Yes, exactly. You can see that the character and the pattern of the line is the same, and this tells you that we have what we call a systematic difference, and this tells you that it's not a difference in nature, but it's a difference in the technique. or say, yeah, a difference, as you said in the beginning, a difference in the sensitivity of the sensor.
But by looking very carefully at the data from the sensors and by comparing the different sensors, you've got a sort of detective trail, and you can work back so that you can find what the original measurement should be, and that's what we can see here.
Yes, exactly. That's what we can see here. That's what this curve is showing.
And so you can trust this data because you've checked it in lots of different ways.
Exactly, it's checked in lots of different ways. We've been done some careful statistics on that. We've compared that to a reference objects on the ground that we know that they should have this and this reflection detected by the sensor.
And then this data here, once you've done this intercalibration, you trust this data, and this is then what goes to, this is fed out as a data product.
This would be what is called an essential climate data record. So this is what the satellite is actually measuring. It's not yet a geophysical parameter that someone can work on and see, okay, this is how the ocean color has changed. But from using a data record like this, we can apply an algorithm that is stable. So the scientists have decided, okay, this is the one we're going to use for the reprocessing of this time series. We're using only this algorithm to reprocess the entire time series, and the result of this will be a climate data record.
So the crucial thing here is consistency, that everyone looks at the same data set after it's been checked and checked.
Yes.
And this data set is consistent with all the measurements that you have.
Yes.
And this is the one that we trust.
Exactly, that's what we need.
And you need that over long time periods because nature might be changing. So tell me a little bit about that.
So nature is changing, and so this is also why we make sure that we have this stable algorithm, because we want to make sure we are not measuring a change in the sensor or a change in the instrument, and we don't want to see a change in the algorithm, but we would like to see the change in nature. And over a long time series, some small changes can make a big difference, and this is why we need to be so careful with those climate data sets.
So there are some parameters like sea surface temperature perhaps, which are the average temperature of the surface of the ocean, which are useful for policymakers, for people outside, and they've all been through this process.
Yes, exactly.
And so we can use those to monitor the climate because there's a small number of variables that are like diagnostic. Like when you go to a doctor and they take your pulse.
Yes, exactly. So we have a certain set of geophysical parameters that people have agreed on, and they are feasible to monitor technically and financially. And these data are exchanged, and using these parameters one could draw conclusions on what to do in the future.
And tell me a little bit about the difference between level 1 and level 2 data, because there's different users who might want different things from the data, and you've taken that into account.
Yes, so a level 1 data product would, for example, be an essential climate data record. So the measurements as they come from the satellite, this would be a level 1. And the level 2 would be a data set where the algorithm is applied. So it would be a geophysical variable that people then can work with, like, for example, a sea surface temperature or sea surface height.
So there's raw data, which if you're a scientist and you've got a lot of processing, computing power to use, you might want to really get into the nitty-gritty of that data.
Yeah.
But if you're just someone who wants to know whether to take their boat out today,
then you will go to the level 2. And if you would try to test your new algorithm development, for example, then you could go to level 1 data. The oceans are very important to our climate system because they drive the climate system as a whole. Climate models or even also weather forecasting models would not be thinkable without information about the ocean. And if it comes to the long term, the oceans are one of the most crucial systems we are looking at, because they drive the climate on the long time scales, and they react very slowly, and this is why they are so important for climate monitoring.
So the atmosphere changes very, very quickly, but the oceans store a lot of heat, move around slowly, but they're the power behind the throne, really.
Exactly, so they have the power to change the whole system, and not just for a couple of days as it is in the atmosphere, but, as I said, for a longer time scale, for decades or even longer.